start now with the next module. So far in this course, just to keep some perspective, what have we seen? Module 1 has been on scalars, vectors, and tensors, where we saw how to perform mathematical operations, differential operations, integral operations on these quantities. Module 2 has been to analyze the kinematics of deformation, wherein we saw two main concepts, the deformation gradient or the deformation tensor, as well as the velocity gradient L, which is a spatial tensor, second order spatial tensor, and the deformation tensor F or deformation gradient is partial x over partial material x. So these are the two core concepts, and around that we saw many other ideas that I'm not going to elaborate further. And then we are now starting module 3, which is to look at conservation laws. Mainly we are going to see mass and momentum conservation, or linear momentum, not angular momentum. So why do we need conservation laws, or what is the connection between deformation and conservation laws? What is deformation?
The body is subjected to compression.
Some kind of loading. So you have a body which is subjected to arbitrary loading. So you say loading, which is basically specifying forces and torques. And what does loading produce?
Deformation.
Loading is the cause. Deformation is the effect. Deformation is deformation, change in shape or change in orientation. So you get deformation, which might be in the form of change in dimensions, shape, and orientation. And if the loading is also, there is loading plus there can also be motion. So remember, motion is P of x comma t, whereas deformation or loading itself is P of x. Sorry. In general, phi of x comma t is motion. That includes deformation. I'll step out of the way. So this is where we stand. We have been studying how to describe deformation, and now we are starting to ask the question, what causes this deformation? What causes deformation? Well, of course, the answer to it is a certain loading pattern. Without loading, you can't have deformation. So now we have come to the point we are going to talk about that loading. Okay, and when you discuss physical principles or basic laws of physics applied to describe engineering loading, or not, I shouldn't say engineering loading, I should say to describe engineering problems or applications. So what do we know about basic physics? You know, mass is conserved. We are talking about classical physics. We are not going to go into any nuclear, energy to mass, mass to energy conversion, that kind of stuff. At least within classical physics, we know you can neither create or not destroy mass. So mass is conserved. And you also know something about forces and momentum. What is that you have learned probably from middle school about forces and momentum? What laws are known to govern the force and the response of a body to a force? Newton's laws, right? You talk about relation between force and acceleration. What is that? Newton's second law, m times a is equal to force. Of course, you also have Newton's first law, which is about inertia, and then Newton's third law, which is about action and reaction. So when you are taking a body or when you're taking a component and you are subjecting it to loading, you have to adhere or you have to use these principles to describe how that loading will cause a deformation. So the whole objective or the aim of this unit is to have a relationship between the loading and the subsequent deformation. Okay, so far it has been almost fully mathematics. This first unit is just mathematics. Second unit is, I told you literally several times, don't ask me how the deformation happens, it just happens. Here is the function, now do some more mathematics. Now we are starting to describe where do we actually get the relationship which is used to calculate the deformation gradient or the velocity gradient. That comes from basic laws. Okay, so we are going to see, so we have learned to describe the deformation of a particle or deformation of a body in two ways. That is, we have our material or referential description, and then we have our spatial or deformed description. I'm summarizing what you know already from module 2, where we talked about a particle denoted by x, a position denoted by lowercase x. What is uppercase x? It is the sum, it is the union of all the positions occupied by the particle, whereas x is just a point in space. Okay. And then we also have a quantity g, which may be expressed in the material form g of x comma t, or in spatial form g of x comma t. Can I erase this side? Anybody wants to? So we want to see these two principles, mass conservation and linear momentum conservation, expressed in material form and spatial. Let me give you a very simple example to begin with to kind of set the discussion. We're talking about mass conservation. Okay. How will you state it very simply? Mass cannot be created or destroyed. But this is a general principle. I'm asking you to apply it for a specific system. And in our case, we'll take that system to be a baseball ball. So you hit the ball across the park, you are describing its motion by specifying the position at every instant of time. How will you state mass conservation for this baseball? Is the mass of this baseball changing as you observe it in your video camera or with your eyes? No, right? Are you okay? Yeah, I'm sitting. Okay. So how will you state mass conservation for a rigid body like a baseball? If you just say one word, should I fill up or complete the rest of the sentence?
Energy equal.
See, we are talking about mass. The ball is hit across the park, so you know the ball is going from position to position. Mass conservation is simply saying the mass of that particle, which happens to be a baseball, is constant. So what is the statement of mass conservation mathematically? Whatever you say in words, how will you write it as a mathematical equation?
Constant all over the time.
Right. So how do you define particle? How is the particle defined? It is a set of atoms which you designate as a particle at the beginning, which we will do it for a baseball ball. So at the start, you call this spherical object with a certain radius, you call it your particle. And what is happening to the mass of that particle, assuming it's not evaporating or disintegrating or whatnot, the mass is just constant. So it's as simple as writing m of the particle at any instant is equal to the mass of the particle at time zero, which I will denote as m naught. So you can write mass at any position is equal to m naught. That's it. I just wanted to start off with a very simple example of stating a physical principle in material coordinate that mass is just constant. Okay. So with that said, we want to, at least for this unit or this module, the goal is to derive mass conservation and momentum conservation in both material and spatial form, which you can use for problem solving. So the spatial form is something like this. You might have seen this. You might have seen this in fluid mechanics or solid mechanics. We are just going to see how this will be derived from basic principles. Okay. We are also going to see we are also going to see how we will derive the momentum equation in spatial form. I'm just throwing this equation to you directly, but there is a neat derivation which we will see, because once we see this, it answers our original question, which is what causes deformation? That is the original question, right? So if you apply a load by either a body force or by specifying some kind of a stress distribution, the effect of that. So treat the right side as quantities that you get to control in an experiment or a loading situation, and the left side is the response of the material to that loading. So this comes down to solving equations, differential equations, where you specify the equation and the solution will tell you how your material will respond to it. So when we talked about the spatial x, material x, deformation gradient, velocity, and velocity gradient, the question is who sets these equations? Where did these equations come from? That was the basic idea which we kept ignoring. But now we have come to say that if you solve this equation by specifying, so these are set externally. That is, you set these parameters. Like when you do a material testing, what are you doing? Sorry. Need to silence my phone. When you are doing material testing, you tell me what is it? What is material testing? You make a sample. People who do material science like fracture mechanics or understanding how ceramics or polymers or composites or metals, they if they are studying different types of materials, your what is your protocol? First, you make a sample. It can be like a simple rod, or it can be a dog bone shaped piece that you put in a testing machine, and then you subject it to loading. Would you agree with me? You subject in your case, it could be like a block of concrete or rock that you put under a UTM and start crushing it, right? So you subject it to loading, and what do you look for when you are subjecting it to loading? Deformation, and you are also monitoring the force transducer in your loading machine to see how much force are you squeezing versus how much is the length changing until something breaks, right? So that loading, you should understand, is set by you. You get to operate the testing machine. You get to say how much force to apply to squeeze that sample or to pull apart the sample. So this is set by the user, and this is the response of the material. Rho, V, X, they are the response of the material. Okay, and from then, when we connect this to the attributes of the particle, finally F or phi are derived. So we have now come to the part where we are starting to understand or starting to describe how these equations come about and then how we will use them. Okay. So in this unit, I'm going to discuss section 4.1 and 4.2. So 4.1 is conservation of mass, and then 4.2 is conservation of linear movement. So these are the only two sections we'll be discussing. Because after this, we have angular momentum, which is sort of complicated, but it doesn't include any more new principles. And then there is energy conservation, which is chapter 5. Okay? Or next module, module 4. All right, so we begin. So this is all sort of like background. I'm going to keep this table here because every time I finish deriving an equation, I'm going to come and put it here so that in the end you will have one table to see. I don't want to photobomb you. I don't want to come in front of the camera when you're taking pictures. I'm going to erase these, keep it blank, and start filling them one by one. All right. Section 4.1, conservation. So let's say we have a body. It initially has a configuration. We'll call it B naught, and it has a surface shape. We'll call it partial B naught. And this is our particle or material particle. Okay. Now you can write M naught at configuration E naught is equal to the mass at a later configuration E. That is, even if this object changes shape, which becomes partial B and B, it still has the same. So this configuration or reference configuration, we'll call it E naught, and deformed or current configuration, we'll call it E. Mass conservation would obviously imply the mass of the material particle remains constant. That's what this statement means. Okay, this is for the entire body. It's easy to say mass is constant, but that is not always the quantity that you need, because you do know that, of course, you take, let's say you take a piece of metal, little blob, and you hammer it and you flatten it into a coin or a disc. Of course, the mass is constant. When you are hammering it, the shape was kind of irregular, but the hammer's purpose is to flatten everything, make sure it becomes uniform and a disc shape. Unless you put this in a heating in a oven and something evaporated, assuming nothing of that was done, the mass is conserved. It's not the total mass that we always care about. It is the change in shape. It's the deformation that we care about. Correct? So this equation by itself is not very useful. We need a more space resolved form. It has to be written as a function of position so that you can do some kind of analysis with it. Am I making sense to you? Just saying mass is conserved is correct but useless. Okay. So if I take M naught at configuration, reference configuration E naught, can I write this is integration over E naught, rho naught, dV naught. This is like writing density multiplied by volume integrated over the shape of the material particle. Okay. You can also write M at the deformed configuration E is integral over E rho dV. Rho dV. And we already made the case that the mass is conserved. So you can write integral rho naught dV naught over a shape that is E naught is integral rho dV over a shape which is E. Now remember, E naught and E are different shapes. They are not the same shape, so the integration limits will change. It's like initially you have, for simplicity, let's take a sphere, like a little marble or little ball of metal, and you are given a hammer and you keep tapping it until you flatten it into a disc. So in this example, E naught would be a sphere. So the integration would correspond to a sphere, whereas E will be corresponding to a disc of certain radius and thickness. Okay. So E naught and E are different shapes. Shapes or integration domains. Volume integration domains. But their integrals are equal, so we are allowed to write this rho naught dV naught integral E naught is equal to rho dV over E. And what do we know about rho? dV? dV is equal to J dV naught at a point defined by X. Where am I getting this from? Comes from the basic idea that F is equal to the gradient of the spatial vector with respect to the material vector, and this leads to J, which is determinant of F, and we saw this in the previous unit. that J is the factor between the deformed volume and the reference volume. Okay. So we are using this relation dV equal to J times dV naught to write want to use this today. Yeah, we can use this. To write integral E naught rho naught dV naught minus integral E naught rho J times dV naught. Right, rho the material coordinates. So this is integral over E naught dV naught times rho naught minus rho tilde times J equal to 0. So what is rho tilde? So you can write then, so if you call density is a quantity or a scalar of interest, you can write rho is equal to rho of x is also equal to rho tilde of x, which is also a function of x. That is, x refers to position. I'm repeating myself, I've said this few times before. X refers to position. Material X has a complicated definition. It is like saying it is all the positions which belong to the particle, and all the positions are again denoted by spatial X. Okay. So I can write rho naught. So if this integral, okay, first of all, two things. One is I keep writing this integral over E naught. Some of you might have already figured it out. This integral over E naught stands for a volume integral. Okay. Second thing is if the integral over a volume of some quantity is 0, the only way that is possible is that the quantity has to be 0. The integrand or quantity that you are integrating over a volume has to be 0. So if I write rho naught minus rho tilde j equal to 0 at all points that on or in E. E naught is one arbitrary reference volume. It's like saying this quantity is 0 at every point. Only then this is possible, because this is integration over volume and it has to satisfy this. So this rho tilde means this is a material representation of rho. The corresponding spatial representation, the corresponding spatial representation would be rho of x. So this statement is basically like saying rho naught equals rho times j in spatial coordinates. What is rho naught? Rho naught. So just to make it easier to understand, rho stands for rho of x it is the density at x, where x is just a reference to a point in space. J, which is determinant of f, is the Jacobian. You can start calling it, Jacobian is just a name. Jacobian was the name of the guy who came up with it, so it stuck. But I would call it volume projection ratio. It is the ratio at which volume scales when you undergo a deformation. So the Jacobian at x and rho naught is the density at x before deformation. So if you are asking for the spatial version of this equation, that is this is the integral version, and this is the spatial version. I shouldn't say spatial version, that can be confusing. This is the equation applicable for a point, for any point in the object or body, whereas this equation is applicable for the entire body. I made it cluttered, I apologize, but these two right here, this is your money shot. That is, after this, you may even skip all this derivation, but the principle you need to understand is that here is mass conservation applied for an entire body. Here is mass conservation applied for any point in the body. So yeah, I'll wait till the pictures are taken. So this equation here is equation 4.1. I'm going to write it here. Equation 4.1, J times rho equals rho naught. This is mass conservation in material coordinates written at every point for a particle. If you want, I'll write it here, mass conservation in material coordinates valid for every, or valid for any point, valid at any point in a particle which we define by the particle vector or material vector x. So we have accomplished 1 out of 4. One of the things which we set out to derive. Are we good? Is it kind of giving some idea that here's, think about that 2 examples I told. First example is the baseball, which is the simplest case, rigid body, no change in shape. What is the mass conservation? M equals constant. There is no difference between the reference configuration and deformed configuration and everything. M is constant. If you have a example, like you take a blob of metal, you deform it until you turn it into sheet metal, like a coin. Even in that case, mass is constant at every instance. You take your hammer, before you start beating it, mass is m naught. You keep doing this hammering, and every instant you go and check the weight wouldn't have changed. It's like saying m naught is equal to m for any future instant. You with me? That information is correct, but useless. because it is for the entire object, which has no kind of information about what goes on at every point in that object. At every point in the object, the reference density scales by the factor J, which is described by the deformation mapping. So this relation is applicable at any point in that little blob which you are hammering into a disk or a sheet. Okay, so this is the summary so far. So now we want to derive the corresponding spatial form. So while you are doing this in a material or a particle perspective, there are some times where you don't care about the finite particle, but you are caring about the what happens in a material as a function of position. Suppose you are doing a FEM simulation. Have you heard of it before? So FEM simulation, wherein you subject a beam to some kind of loading, and you are trying to calculate what is the strain in some section of the beam. There you need a description which is different from this one. You need a description that is based on position and position in space than about position within a particle. That is why we have the spatial reference coordinates, the spatial coordinate system, and we want to write this equation in that spatial form as well. That's our next subtask. Are you guys with me so far? You're okay? All right. Okay. All right. So we'll start with J rho equal to rho naught. Okay. So there is the reference configuration which we'll call E naught, and then there is any other configuration, or to kind of keep it closer to our example, we are kind of making it into a disk by hammering. We'll call that E. Okay. You can calculate m dot of E, which is the rate of change of mass within E. M dot is the rate of change of the mass, which is expressed as integral over the volume multiplied by density at each point times dV. Okay. But what is the deal about mass? Will it change over time if it is constant? You wrote mass as constant throughout the loading process, right? Unless we have some funky physics going on, which we don't. This m dot, you don't have to do a lot of thinking to say, is actually zero. Because mass is constant, its rate of change with respect to time has to be zero. So this is like writing integral over E, or d dt of integral over E rho dV equal to 0. So I want to recall that Reynolds transport theorem, which we quickly saw at the end of last lecture. So recall Reynolds transport theorem. You write any quantity I is integral over the volume g of x comma t dv in general, where g is generally a function of space and time. Here we can even write rho of x comma t dv. If I is a quantity which is the integral of g over a certain volume, then I dot, the rate of change of I, is given as integral over E g dot plus g divergence of V dV, or it's also equal to integral g dot dV plus integral over the surface g V dot n dA. We can take either form. They are both equal. This is like in the volume form, this is volume plus surface. Like what's going on inside versus what is crossing the boundaries. Okay. So this you can just, this holds true for any quantity, in just that our G is now rho. So I'm going to use this result here to write rho dot plus rho times divergence of V integral over E dV equal to 0. Clear? Yeah. So I dot is d over dt, d over dt integral g of x comma t dv, and of course there are steps in between, which is what RTT proof is about. That's, we already saw that. So now we are just using this result over here. So look at this statement. Integral of this quantity rho dot, which is like writing the partial derivative of rho with respect to time, rho dot plus rho times del dot v dv is equal to 0 over the volume. When is this possible? When is integral of something over the volume equal to 0? If this quantity has to be 0, what is the only way that can be 0? Um, so you are thinking this is going to 0. Like if you say dv is dx dy dz, you are arguing let's make dv 0. That's points to you for lateral thinking. But what we are trying to say in general, that is a very special case. In general, if this integral has to be 0, the only way that's possible is this function to be 0 at every point. So integral E rho dot plus rho divergence of V dV is 0 implies rho dot plus rho divergence of V equal to 0 at every point in E. Okay. So this expression here, rho dot plus rho times divergence of V, this is the spatial form of mass conservation. At every point, this relation must be satisfied, period. So if you are doing your hammer example, you can, in principle, it's not easy by any means to do this in practice. In principle, at every point in this object, you can apply this principle and calculate how the density at a point evolves over time. If you know the velocity, if you know the initial condition for density, you can solve this as an equation for rho as a function of space and time, like saying at every point you can say how the density changes as a function of time. In principle, in practice, if you want to solve this, you can't solve this without knowledge of what is B. So at least you need one more equation to solve this problem, which comes from momentum conservation. So we are going to see that. So at least in the spatial form, the equation is partial rho over partial t, rho divergence of V equal to 0. You know how to write this in index form. It's not a difficult thing for you to do. So I'll just leave it here. And this is equation 4.2. Equation 4.2. And erase this for removing the clutter. What I said here is valid. Okay. So this is one way of writing the spatial form, but not the only way. We'll just see how this can also be written slightly differently using the same quantities. Okay. So to do this, we want to go back to what we already saw, but sort of saw quickly. So if you have a quantity G, which is expressed as G tilde of x comma t or G of spatial x comma t. This is like any function, either in spatial or material form. We have a functional form for that. What is the rate of change of G? Rate of change of G with respect to time. That is this quantity. When we write G dot, it usually means with respect to time. In the spatial coordinate system, this is dg over dt for a fixed material particle. The only complication is your material particle is sometimes very hard to define because it has its own shape. It's like saying you have to evaluate the time derivative of this function over a particle whose shape itself is not simple. Okay, which we can write is equal to partial g over partial t plus partial g over xj multiplied by xj, which is a function of x and t over time. It's easy to say in words, that it is over a fixed particle. But what defines a particle? The position of the atoms define a particle. I'll put it down in writing. What defines a particle? X. The position of the atoms that constitute the particle. So if your particle has deformed into such a shape that it looks like a donut with a hole in between, your particle is the donut, but not including the gap in between. That is not your particle, even though that volume is between your particle, it's not your particle. So this calculation is actually very difficult in practice, which is why we never do it. We switch back to the spatial form where you can get a derivative of g with respect to time for a constant position in space multiplied by the derivative of g with respect to the position multiplied by the rate at which the position is changing. This equation here what is this quantity? This quantity, you know this, you said it. Velocity in material coordinate is the first derivative of spatial position. Right? Once you know the velocity in material coordinate, you can easily write this in spatial coordinate. You have to use the transformation. Okay, so we will write this plus g over xj multiplied by vj, vj of x comma t. So you can also write this equal to g dot plus the gradient of g dot velocity. So moral of the story is g dot or I'll write it dg over dt is equal to g dot plus gradient of g dot v. The reason I went back to dig up this result is I need it. I'm going to need it. I'm going to use it here to get a slightly different form of the mass conservation equation in spatial form. You have a question? Something's not clear? So if we take G to be our density. Okay, so you'll have G dot equal to rho dot. What is dg over dt? That will be that will be rho dot plus gradient of rho dot v. So not clear. Okay, I'm at a little loss here about one step that I kind of missed in between. I don't know where, but I hate to do this, but what we need here or what we'll get as the alternate form is this multiplied by rho b equal to 0. That is, instead of writing rho times del dot b equal to 0, you can show that these two forms are equivalent. But to do that, there is a step that I'm kind of currently not able to place. What is that step? So if I take this equation, how will you expand this divergence of rho v? So what is divergence of rho v? That is partial over xj of rho vj. Right? So this would be partial over partial t plus partial rho over xj vj plus rho times partial vj over xj. So this is partial rho over partial time plus gradient of rho dot v plus rho times divergence of v. Okay. So here's what the book exactly says. The book wants us to use this result in this equation to derive this. And I did this when I was preparing for the lecture, but I seem to have lost my step here. Can anybody see what we are missing? So if you mean we believe this equation because we derived it from we derived it before we got into this. So from this equation, you can take the derivative with respect to time to be the negative of this one. All right, I'm going to see how I can reconcile and give you an explanation by next lecture. But without wasting time, I want to present to you two equivalent forms of the spatial form of the mass conservation. This is the equation 4.2 and this is equation 4.3.
I think that might be a dot product identity.
Come again?
I
Sorry.
think it might be a dot product identity number 4.
C A dot B is C times A dot B plus A or equal to A dot C. So if that is true, dot del dot rho v, del dot rho v, you're saying is equal to,
I think they're just based off of that thing.
so yes, I mean, this identity basically means del, if you treat your del like A, del A is del, the operator, dot rho is your C, the scalar, and V is the B. This is equal to rho times del dot V. Can we prove this? Like, can we, all of us together, can we prove this using index notation? I mean, that's literally what we are doing. We are replacing this with this. The other term is remaining same, so these two have to be equal. But I'm just asking how? Can we prove it? Okay, let's not, let time pass. I will ask you to think about this. Okay, think about this. We will try to get an answer by next lecture. But for now, we have seen mass conservation principle both in material form and spatial form. Can somebody tell me when you will use the material and when you will use the spatial form? That is, when you will use this one and when you will use either of these two. What is the basic difference between this type of an equation and this type of an equation? This is applicable at any point in the body, but if you look at it, it is an algebraic equation. It involves J at every point. It involves rho at every point and rho naught at that point. You are not integrating anything. You are just calculating. It's like saying if the density at that point went down or went up, it has to be scaled by the J value. Look at this equation. What are the quantities here and what is the nature of the equation? This is algebraic and this is what? A differential equation which connects both time derivative and spatial derivatives with the quantities rho and v. To solve this equation, if you have a differential equation which involves time and space, what is it called in mathematics? If a differential equation involves only space, suppose you have a bar, it is supported at both ends, you specify some loading and you have to calculate deflection. You have done this type of problems. EI d to the 4 y dx to the 4th equal to some force distribution. This is a differential equation. It needs to specify two things. What are those? You need to tell what are the boundary conditions, right? If a differential equation is about spatial coordinates, you have to tell what happens at the boundary. And if it involves time, you have to tell what was the initial condition. And if it involves both time and space, you can call it an initial boundary value problem, where you have to specify what is going on at the boundaries and what went on at time 0. So you have to solve this equation, and to solve it, you need to know initial condition, boundary condition. And not only that, this is just one equation, but involves three variables: density and three components of velocity. Okay. You should first recognize that you can't solve this equation by itself unless you know velocity from somewhere. So the key difference is, the first thing I said, this is an algebraic equation and this is a differential equation, partial differential equation involving time and space. That is just an observation. You tell me, where is this equation or which situation is this equation more convenient and this equation is more convenient? This involves time, right? Does this equation involve time? Doesn't look like it involves time, but that is that everything to it? Is there something more to it than what you write here? Rho is a density which could be a function of both position and time. So it's still an algebraic equation, but it could still have a time dependence. So don't think it is independent of time. Number one. This is applicable at any point. And if you are given some sort of constraint about the material, if the J value is calculated through the deformation mapping and you know the J value, this equation is really simple. It's like saying at every point, J is just the scaling factor between the reference density or the density at that point in the reference configuration versus the current deformed configuration. It is still a useful equation for finite sized objects because every point in a body, it has a reference shape. Every point in that shape will find a point at a later deformed configuration, unless there is a mass loss. You take your example about the hammer and the blob of metal, and you keep striking it and flatten it. Every atom in that initial blob has been relocated somewhere in that disk. So this equation is applicable to every point of a finite sized object. When we write this equation in the spatial form, we generally write it for a domain like a beam or a disk or a plate or a sphere or some kind of shape. And this is a differential equation, meaning it is defined at every point, and the resulting solution is also defined and analytic at every point. This is the basic thing we saw at the beginning of the course. These functions have to be analytic functions. They should have derivatives, they should be continuous, they can't be ill-defined. So when your interest or when your goal is to calculate quantities for a finite sized object, you would go with the material description. When your intention is to describe what goes on at a at the spatial level in a body that is continuous, it could have boundaries, but what is the difference between a finite size and a differential or an infinitesimal? If you take this object, if I keep chopping it, I'll get half, quarter, 1/8, 1/16, and so on. The length will keep shrinking. At one point, I'm going to run across to a size like a thickness that is same as the blade which I'm using to cutting it. If the thickness of this object becomes shorter than the blade, that's it. I can't cut further. Okay. So as long as the object seems finite size to your length scale, you can keep applying this relationship. What is the difference between this finite sized object and this equation? What is the basic tenet of calculus when you think about differential equations or differential volume or differential length or differential area? What is dx? In differential calculus, you always start with you have a point x, and a little later you have a point x plus dx, and you say this length is dx, which is sort of x and another point that is really close to x. How close? You can make it arbitrarily close. What does that mean? Is it a centimeter away? No, it's less than a centimeter. Is it a nanometer away? No, it's less than a nanometer. Is it a picometer away, which is 10 power minus 12 meters? No, it's closer than a picometer. You can name any length, and I would say it's even closer. You may ask the question, does it even make sense to talk about 10 power minus 18 meters? Because it's basically the distance between a nucleus and an electron cloud. I don't care, because my continuum assumption is that this whole continuous media is a fictional material which is infinitely divisible. That's where we started the whole course, right? You talk about a continuum or a continuous medium, which is infinitely divisible. That is a model or approximation or a version of reality which doesn't really correspond to reality, because reality at one point starts becoming atoms and molecules. It doesn't behave like a continuous medium. So whenever you care about describing a material within the framework of continuum mechanics and calling it as a continuous medium, you use the spatial description. If you are just looking for relationships between the density or any quantity at a more macroscopic level, macroscopic meaning quantities which are easy to measure and which are not flirting with the idea of continuous medium, which are not tiny distances, then you use the material frame. Again, whenever you are dealing with solid mechanics, people deal with material frame because in solid mechanics, two things. One is usually the material, the material does not flow with a big velocity. You take your example of a blob and hammering it down. The atoms are relocating, but they are not moving awfully fast. You hammer it once, they would have moved a little. Hammer it again, they would move a little bit more. But between your hammering, they are pretty much static. You repeat the same experiment with a liquid. You take like a bucket of liquid and you drop a hammer in it. That liquid will pick up the momentum and will splash out. It will flow as far as it can. And in that case, it's better to go with the spatial form because this is more open for time or time dependent behavior or fluid like behavior. So more suited for fluid like behavior and also for continuous medium. Whereas the material description is more suited for solid like behavior. By solid, I mean, what is the difference between solid and fluid? A solid kind of preserves its neighborhood. If you are an atom in a solid, your neighborhood over time looks pretty much the same. You don't get a lot of mobility to keep moving around. If you move around a lot, that would be fluid-like behavior. Okay, and for finite sized objects, which you may call particles. Okay, so everything that I discussed today is under section 4.1. Okay, and my goal is, so we did mass conservation today. I have about like 5 minutes. I don't want to just start a very new topic at the last 5 minutes. So we'll stop here. Couple of housekeeping things. I plan to take the next 3 lectures to discuss the remaining topics, which includes basically module 4, first law of thermodynamics for energy conservation, and that will wrap up the course. So I have posted the homework which you can start attempting, and hopefully by next lecture you should be able to attempt the homework more. And I'm hoping that next lecture I will wrap up this, and the third lecture I'll do the first law of thermodynamics, leaving the last lecture for discussing the homework and some additional problems. And then you get a day more to complete the homework and submit. That's the plan. And the exam will be posted around April 30th with 1 week to submit. Is that clear? Any questions? Okay. Thank you. We'll meet next lecture on Tuesday.